In this short presentation, I'm going to explore the current scientific understanding of the relationship between crater morphology and regolith composition on the lunar surface. I'll touch on what I mean by crater morphology and regolith, and explain why this is an important area of study. The first thing to know is that lunar is a Latin word for moon, and this is the term I'll be using today. Craters are the holes or cavities seen on the lunar surface. Craters are formed when meteors, that is, space rocks, crash into the surface of the moon. These craters can be described by their shape and by various measurements, such as their depth, diameter, the angle of their internal slope, or by the ratio of these different measurements. The most common example of this is the depth-diameter ratio, where we divide the depth of a crater by its diameter. Both crater measurements and their shape fall under this broader category we call crater morphology. The shapes of craters can be categorized into several categories: normal craters, which are bowl-shaped, flat-bottomed, concentric, and central mound. Meteors impacting the moon are assumed to only impact the top few layers of the moon. The moon has many layers, the top of which, in most cases, is called regolith. The regolith is assumed to be above a harder layer called substrate. So, what is regolith? Regolith is a thin soil that has a similar consistency to the topsoil you might put on your garden. Extensive chemical analysis of Apollo mission samples retrieved last century have shown that regolith is made up of many compounds, primarily oxides. These include silicon dioxide, ferrous oxide, titanium dioxide, aluminium oxide, magnesium oxide, calcium oxide, potassium oxide, and sodium oxide. So, now we ask the question, what relationship exists between crater morphology and regolith composition on the lunar surface? Now, the answer to this question is not yet fully known. No studies have been published that show a relationship exists between crater morphology and the chemical composition of lunar regolith. However, several studies have been published on other topics related to crater morphology and regolith. Primarily, mathematical models have been determined that infer the depth of lunar regolith based on various crater morphologies. And secondly, some studies have been completed that analyze the relationship between crater morphologies and different lunar terrains. So firstly, let's dive into exploring regolith depth and its relationship to crater morphology. This topic was first explored in 1968 by Quaid and Overbeck's paper that is commonly cited for proving craters are caused by impacts. They conducted experiments on Earth using projectiles made from aluminium, Pyrex glass, and Lexan into a faux regolith in substrate layer, made of sand and epoxy resin. They compared the morphologies of the experimental craters to the images taken by the lunar orbiters 2 and 3. They found a relationship could be derived between crater measurements taken and the depth of the regolith layer. In 2011, using new data from the Lunar Reconnaissance Orbiter, Bart et al. Updated the equation from Quaid and Overbeck's findings to the equation seen here. The regolith depth, called thickness, is equal to 0.86 minus the diameter of the inner feature over the crater's diameter, all multiplied by the crater's diameter and the tan of the angle of repose of the regolith, all over 2. In 2014, Bart herself improved the accuracy of this equation by calculating the diameter of the inner feature from the base of the crater wall slopes. In 2016, more accurate measurements taken of the edge points of craters reduced areas and measurements caused by undulation outside of the craters. Now, this equation is not a one-size-fits-all solution. The equation best predicts regolith depth for craters where the diameter of the inner feature over the diameter of the crater is between 0.2 and 0.7. Additionally, there is now evidence to suggest that multiple low-velocity meteor impacts could cause normal, flat-bottom, and central mound craters in the same way a single impact could. It is now suggested by some in the scientific community that the equation be only used to predict regolith depth near concentric craters. Now, let's discuss the varying crater morphologies based on location. The darker areas of the moon that we see with the naked eye are called the lunar maria, and the lighter regions are called the lunar highlands. There are distinct differences in crater morphologies in the Maria and in the highlands. Craters less than 4 kilometres wide are deeper in the Maria than in the highlands, but craters wider than 15 kilometres are deeper in the highlands than in the Maria. For craters with a diameter between 1 and 16 kilometres, the median depth-diameter ratio is greater for Mare craters than it is for highland craters. On average, Mare craters have a depth-diameter ratio greater than 0.1, whereas most highland craters have a depth-diameter ratio less than 0.1. And it turns out the crater density in a region also impacts the depth of craters. Deeper craters are formed on younger surfaces with lower crater density. Now, a study by Bo Wu et al. In 2022 suggested that differences in depth-diameter ratio can be found above and below a line of 60 degrees latitude. However, different instruments were used to calculate crater depth and elevation either side of that 60-degree latitude line, so it's not clear whether a distinction does exist. So, why is studying a relationship between crater morphology and regolith important? Many space administrations, including the Chinese National Space Administration and NASA, plan to build lunar bases and use in-situ materials. Knowledge of a relationship could influence decision-making for the location of these bases. Since regolith depth can be determined by crater measurements, we can therefore determine how far below the surface the harder substrate layer is. When building bases on the lunar surface, it will be important to build on a solid foundation. The deeper the regolith is, the more effort required to excavate that regolith, or the more materials we'll have to use for structural support to go through the regolith layer into the substrate. Additionally, for in-situ resource utilization, if we know a relationship exists between crater morphology and chemical composition of that regolith, we can choose a lunar base location based on the location of resources we wish to use. To recap, we have asked the question, what relationship exists between crater morphology and regolith composition on the lunar surface? We now know that regolith depth can be mathematically determined based on the measurements of concentric craters. We know that crater depth varies between the lunar highlands and the lunar Maria. But there is no currently published studies showing a relationship between crater morphology and the chemical composition of lunar regolith. Knowledge of a relationship between crater morphology and the composition of regolith may prove useful in choosing the location of future lunar bases. If you'd like to learn more about this topic, please feel free to pause the video and have a look at some of the sources used to create this presentation. If you have any questions, please feel free to get in contact. Until next time, keep looking up in amazement of our wonderful universe.